Okay, I'm going to start with chapter 4. This is part 1 of 2. We're looking at mechanics, engineering mechanics. Okay, and basic definition, we can say it's a study of state of rest or motion of bodies subject to forces. So any object, any real world object, is subject to different forces that are acting on it. And these forces, if they're so-called balanced forces, where they're equal in all directions, it's considered to be in equilibrium. Okay, so like a table is just stationary, at least relative to the room that it's in or the building that it's in. All the forces, if you drew vectors, or if you drew, the directions plus all the forces acting on it, you would say it's in equilibrium. So like a table would be, whatever the force of the weight of anything on the table pushing down is going to be equal and opposite of force of the floor pushing back up. Okay. So what we're going to be looking at is, in our case, we're going to be looking at the so-called equilibrium cases. Okay. So that we're going to be essentially we're going to come up with a system, and we're going to use vectors. Vectors are just basically vectors are quantities essentially that you think about that have two components. They have direction and magnitude associated with them. Okay, so that's what we're going to do. We're going to be looking at mechanical systems that are at rest, at least for this course in this chapter. Okay. Just a little bit more information. In general, engineering students, you're going to take a course in statics and another dynamics. And the difference between these two is that statics means that all the forces acting on a body, any kind of rotation on a body, it would all sum to zero, right? So it's essentially stationary, right, for the most part. You can also think of statics as being a situation where you have like a car traveling down a flat road, not changing elevation at a constant speed. All the forces would be equal in that case also. But for the most part, most of the things we're thinking about are stationary, all right? In dynamics, the difference here, the main difference, is that you have some acceleration, okay? So it's not at the same velocity all the time. You're accelerating. So dynamics adds that other component, all right? But for us, when we're talking about statics, at least in this chapter, we're really talking about a system that's stationary also. Okay. Okay. So principal mechanics use to design, analyze about every kind of engineering system, right? We need to be able to know. So, some kind of physical system, we have to know something about it in terms of like its motion potentially, or the forces that are acting on it and how that impacts its motion, if there is motion or not. Okay. Or, if there's acceleration, right? Okay, so one of the ways you could break up mechanics is using this diagram, and through the different categorizations, you'll see that over here is rigid body mechanics, solids, statics, and dynamics. Then if it's deformed, the body can deform. You also have, and we're going to look at this a little bit too, where bodies deform. Okay, under forces. And you also have fluid mechanics here. Okay, so we'll look at all of these a little bit, mostly kind of over here in the statics range, but we will look at all of these just to kind of give you an idea. In this chapter, we have to think about these deformable bodies also. So if you put something under some force, it's going to deform a certain amount. Okay. And that's where it falls under like stress and strain. Okay. All right. So thus far, anything we've had is like forces. We've have just like a single line of direction. Okay. So if you're talking about like, weight, let's say, right? It's like weight. Yeah, but you could just put it as a single line of direction, pointing straight down, right? But we also have to be concerned with forces that are acting more than just like straight up and straight down, right? All right. And the way to do that, we need to have we need to be able to represent those forces in our three-dimensional world. So we also have to have a directional component in addition to that magnitude. So even weight, what's the direction? Well, it's straight down, toward the center of the earth, right? Well, that's an equilibrium condition, if you're just standing in one place and not, going up and down in elevation, is that you would have a force of the ground pushing back up that would be equal and opposite. Okay, so you can remain stationary that way, right? But we have real world problems that are more complicated than that. We may have, multiple cables holding up a light fixture. We may have a roof being held up by, vectors, by supports that are not, vertical, straight up and down. They maybe have angles associated with them. If you look at bridges, you can see bridges that you have like truss bridges are a common thing, or cable bridges. Like cable stay bridges or suspension bridges have multiple forces acting in different direction. We have to take that into consideration. Okay. So this brings up this idea of a vector. So what is a vector? A vector has two components to it. A vector is going to have magnitude and direction. Okay, so we have to basically come up with a mechanism to represent our three-dimensional world, right? So we have to have vectors themselves that represent each of the directions, right? Okay, just some more terminology. We started with scalar, and then we have a vector. So, of course, scalar has nothing in it that tells you anything about what direction these things are acting in, right? Like your speedometer in your car is a good example, or temperature, right? It doesn't say anything about direction associated with it. The vector quantity has both, right? So displacement, like location of something, let's say, relative to some point, force, velocity, acceleration, stress, momentum. These all are represented with vectors. Okay, so here we have an example how we could represent that. All right, so let's say that we wanted to come up with a resultant. We have multiple forces acting on some object. All right, and all this really says is that, this should be highlighted here. This A and this B are vectors. And in my lecture notes, you'll see it'll be bold-faced if it's a vector, and not if it's a scalar. Okay, so let me just correct this real quick. Okay, just made that correction. So these two are vectors. All right, so what do you have? A vector added to another vector gives you some resultant vector. Okay, so this is an important thing. It's often the case where you want to take all the forces together and come up with some resultant of those forces. It might be multiple cables connected to an object, and then you want to figure out all those cables put together, what would be the resultant of those? Where would they pull that object off, in what direction, with what magnitude? Okay, so when you're actually writing it, though, it's hard to tell like which is like what's a vector, what's a scalar, and how do you write it differently. Typically what you'll see is an arrow over the top. If you see an arrow over the top, that's another way to represent something as a vector. So if this equation would also show up, another way would be A arrow, B arrow equals R arrow, meaning that vector A plus vector B equals this resultant vector R. Okay, so you'll see that also. All right. Okay, so that's what I'm talking about. So vectors you'll see with a line or arrow over the letter if it's handwritten. In the notes, printed material, you could just use boldface and tell that it's a vector. Okay. Then handwritten. I'm sorry, scalar symbols are just handwritten. And often you'll put it in italics to show that this is just a scalar, just a quantity. Okay. Okay. So if we're looking at like vectors, and what we need to do is kind of break up our space into x and y, right? So this is two dimensions. Of course, we have one more dimension that we need to talk about after this. But the third dimension would just be like straight into the paper, straight out from the paper, okay, from this sheet. Okay, so what do we have? First, we have to identify something as an origin. So if you had a problem, you're working on a mechanics problem, and it might be given what the origin is, or maybe not, but you have to define something as the origin, and everything is kind of relative to that point that you've defined. Okay, well, if we look at this, if we're representing our vectors, and we're breaking it up. So like, let's say that you had a vector that was considered to be, two, 1 unit, or let's say 3 units in the x direction. So it goes off in the x direction. And then it's 2 units in the y direction. You would end up right here. And the vector would be a point from here, which you could draw with an arrow, from the origin up to this point. Okay? So what we need to be able to do is have a way to represent that, right, uniquely. Okay, so we have to be able to represent how far we go in the x direction and how far we go in the y direction as part of the vector equation, okay, which will do that. And the way it's done is they actually have these things called unit vectors. If you have a number and it's multiplied times I, what it is really just telling you, oh, if it's 3 times I, it means 3 in the x direction. And if it's 2 times j, when you're using unit vectors, it just means it's 2 in the y direction. Okay? And it's very important, of course, we have to make sure that when we're talking about vectors, we have to have some information there to tell us the direction of it, right? And we can do that in a couple of ways. And like I said, one of them is just unit vectors. Just do 1, 2, 3 times I. And then the other one for the y direction is 2 times j. Okay? Another way you could do it if you wanted to represent this point, and say a line from here to here, would be to say that the magnitude, how long is this line, and what's the angle relative to the x-axis. Okay? That's another way to represent vectors. And what you'll find is the first way I talked about using so-called unit vectors is easier to work with typically. Not always the case, but you can always convert back and forth between the two. All right. Okay, so you can add a z-axis, and of course that's going to be perpendicular to this plane. It's either coming straight out and going straight in, right? So the positive being straight out and negative going straight in. Okay, so some trigonometry notes. So when we actually go and try to solve a problem, we need to pay attention to this. Okay, all internal angles of a triangle equal 180 degrees. And all angles on one side of a straight line sum to 180 degrees. Okay, so just some additional notes, right? So if you have a straight line and you have some other lines crossing through it, if you did all the angles together, you'd find that it's going to be 180 degrees. All right. So when you're doing calculations, set it to degree mode. Okay. Set calculator to degree mode. Let me write this a little bit differently. Okay, continuing on, I just rewrote this slightly. So when you're doing problems in this class, typically we'll give information in degrees, but you could also do it in radians. Okay, with 2 pi radians essentially equals 180 degrees. So understand you could do both ways. I think all the problems we have will be in degree mode, so you want to set it to degree mode before you perform the trig functions. Okay. One more thing we're going to find it's going to be useful for us as we go to solve problems is this idea of law of sines. Okay. And the law of sines is a relationship between the sides of the angles. Okay. So this is any triangle. While when we use the trig functions, that's if you have 90 degrees. Okay. But this basically what does this mean? It means that side A and this is like our angle over here. So this side A, the relationship between this side and this angle has to be the same as, where B here is an angle here. The relationship between this side and this angle, and which is equal to essentially this side over the sine of this angle. Okay? And it's all equal. Well, equal to 2 times radians. But really what we do is we look at this, this, and this, and these are the ones that we'll use when we want to solve problems, when we're using the law of sines. Okay. Oh, and here's some other trig functions. So if you have 90-degree angles, and you notice this is going to be really useful for us, is like when you're trying to find like these sides. If you think about it, like when we have a problem and we have like a y, maybe this is the y direction, and this is the x direction, that we might be given this length of this, the hypotenuse, right? And maybe we know something about the angle. And if we do, we can actually, here's the relationships between them. We could actually figure out what those sides are. So let's say I do sine of A times hypotenuse, take the hypotenuse, put it over on this side. That will give me the opposite side. So that gives me like basically like the y component, okay, in this case. And then if I wanted to find like this side, the adjacent side, I could just do sine of A times the hypotenuse would give me this, right? So if I took hypotenuse and put it on, multiply both sides times hypotenuse, and hypotenuse would end up on this side. Now there's also a relationship between the adjacent and opposite. Then you would use tangent, okay? So what it comes out is this is one of the ways we can go back and forth, or go forward. So let's say we're given, we could find the angle, depending if we do the inverse sine of the angle A, and then opposite or hypotenuse times the inverse sine of both sides. So that would just become A, which is the angle, would be the inverse sine of opposite or hypotenuse, right? So we can work with this, but these are just the standard definitions for these functions. Okay. We also have the law of cosines is another useful one for us, and this is the same. This is where any triangle will work, but basically it says that if you have a side c squared, a side c, these are your three sides, A, B, and C, and you're looking for, let's say, on the relationship between these. So the square of the C side, whatever it is, whatever side you decide to be that, is equal to the square, the one side, the other side squared, plus the other side squared, so I'll have three sides, minus 2 times AB times the cosine of the angle, which is the angle essentially opposite of this side. Well, if you square root both sides, you can actually find that value of C. All right. And of course, it works for any of them. It doesn't really matter, C, A, B. This is just showing you, of course, that if you were to use it in other factors. And really the key point is this is the angle that's opposite side, essentially what you're looking for. Then you would just, of course, like I said, do a square root of both sides, and you can actually find that side, okay? All right. All right, so this is just the same thing. Okay. All right. So, like I said previously, it's that a vector just has both magnitude and direction, right? And common vector quantities, displacement, force, velocity, acceleration, stress. And two things we're going to use it for. You can actually use a vector to represent like a position in space, like a certain location, or you can actually use it to represent a force. Sorry, we'll do both of those. Okay. So how do we work with vectors? Well, we can't just like do things as we do with scalars, right? With numbers, we can't just add them directly. We have to actually break it up into its components. So we have to add like everything, all of the individual components that are part of the x, and then all of the individual components that are part of the y, so that we can come up with a resultant vector of that problem. Okay. So we'll do that with forces and also in terms of location. Okay, so we'll look at that also. All right. Now, if we want to go in and solve vector problems, we can do we could take one of these three approaches essentially. Okay. Here's the parallelogram method. I'll work through an example to show you that one. Graphically, you can do it, right? You can just add up all the vectors. And I'll give you a quick example of each of these to show you that. But graphically, you can just take arrows and use them and add them together. Often certain, you have an angle and you have a vector of certain magnitude. You can add one to the, head of one to the tail of the other, head of one to the tail of the other, and you can just do this. Graphically is good to get a nice estimate of it, but it's easy to make errors, which can kind of throw off the end result, right? So you can use, like, graphically would mean that, maybe you're doing, you have two vectors. One is 100 newtons off in a certain direction, another one's 50 newtons off in another direction. You can say, like, a quarter inch equals 5 newtons or something, and then just add the two together, and then the resultant one you figure out, and you could use a protractor to figure, from relative to some x-axis, and you can use the final length of that vector, which you've drawn the two vectors head to tail, and they have the appropriate angles. That final length of that vector is going to give you, the length of your result scaled to however you scaled it. Maybe, like I said, a quarter inch is 5 newtons or something. And that would give you the end result of that magnitude. And then the angle, of course, would be relative to the x-axis, positive x-axis, and it would be whatever you measure, with a protractor. Parallelogram method. This one is, we actually like taking one vector, putting it on the head of the tail of another one, and then using, like, the angles, the internal angles, and then coming up with an end result, going through a process. The last one, and this is a bit more difficult than the component. Component method is just taking and breaking it up into, I and j. And if it's 3-dimensional, we have another unit vector called k. But for 2 dimensions, it's putting it into components I and j, add the I components individually, add the j components individually, and then the end result is just, the I components times the magnitudes of the i's times I, the unit vector, and magnitude of the j's times j, unit vector. Okay. So this is just a process of going through and doing it graphically. I'll have to go through and show you an example. So this one is just draw vectors to scale, draw each vector starting at the head of the previous vector, and when done with all vectors, the result's the resultant vector. Okay, so it's not much to that. Either I'll, create one or show you a YouTube video on that. Okay, so this is just graphically using a protractor and ruler, essentially. Okay, parallelogram method. This is going to draw 2 vectors to be added, create a parallelogram head to tail. So creating a parallelogram essentially with, adding the 2 vectors head to tail. Draw a resultant vector, find the angles opposite, so the internal angles. Apply the law of cosines to find the resultant one, and find the angle of origin between the resultant and vector that makes up the triangle using the law of sines. Okay, so these are the steps, and like I said, I'll go through an example with that. And then the last one here is the vector component method, and this one is that you use unit vectors to represent the vector in terms of x and y coordinates. Okay, so the unit vectors are just going to be I, j, and k. So a unit vector is so-called dimensionless. Okay, unit vector actually has a length of 1, but it specifies the direction. If you see something times I, it is going to be, and they're actually, you'll see these bolded also. But if you see something times I, it means that in the x direction, times j means in the y direction, and times k means in the z direction. Okay, and like I said, same thing. We'll do an example of those. All right, so this is what you would see typically, how it would be written when you're using unit vectors. So you have some vector A, and you could break that up into its I and j components. So here is the magnitude in the x direction, and here's the magnitude in the y direction. Okay, so this would be a typical way to see it. Okay. Okay. Just clicking through these. Okay. So here's the vector component method. Just draw the vectors, apply trigonometric functions if it's 3-dimensionally, do the z also. Write it in terms of its unit vectors, add the individual components, and knowing the sides of the apply trigonometric function to find the angle of the result. Okay? And that's good for now. The rest I'll handle in part 2. So, but I will go through and show you, I'm going to back up here, graphical method, parallelogram method, and the component method so you can see those, the different ways. Okay? But recognize that all it is saying 3 different ways to add, in our case, add vectors together. Okay, and it doesn't matter what those vectors really represent at this point, although we'll use them for forces in this chapter after when we talk about forces.